Hey there, welcome to day 2 on limits. We're still in section 2.1 of the limits unit, but now we're going to move on from um, situations where we can evaluate limits just through substitution, which is what most of last night's assignment was, to where we can't do that. As it says on page 3-4 of your notes, limits can be found. Okay, if the function is continuous at certain points. Anywhere your function is continuous, you're just going to be able to use good old substitution. Um, Continuity is a fantastically convenient thing in mathematics and calculus specifically. The question of today is, what if your function is not continuous? Can you still find limits at those locations when substitution is not a viable way of doing it? The very last problem that we did yesterday, problem 20 from your homework, was this problem right here. And what it asked is can this function be evaluated through the substitution? And the answer, if you watch the homework video, was no, because if I put a 0 in here and a 0 and, okay, let's try that a different way. If we put a 0 in here and a 0 in here, I'm going to get 4 squared, which is 16 minus 16. Well, that's going to be 0, right? And on the bottom I have a 0, and so I get a 0 over a 0, and that's undefined. And that's why you can't do it that way. Some people try to tell me this is 0, but unfortunately it's not. So you cannot do a problem like this through substitution. So what are we going to do? That's really the basis of what today is all about. I will give you a hint. I mean, I'll go ahead and kind of show you. It just comes down to being able to apply algebra, because we can manipulate what the top of this fraction looks like. 4 plus x squared is just 16, not plus x squared, but plus 4x plus 4x, right? It has to be FOILed out. So 16 plus 8x plus x squared, then minus your 16 all over x. So what is that? Well, once those 16s cancel, I can factor an x out of what's left over. And remember, the whole problem with this in the first place was I can't put a 0 in the denominator. Guess what? There is no denominator anymore. So now we can just throw that 0 into the function, and that's called evaluating the limit, and you are able to substitute. So the limit here is 8, and if we look at the graph that the function generated, that's exactly what we see. There wasn't a point at 8 because it was undefined. There was just a hole. Okay, and limits don't care about what's there. Remember, that was a big thing that we talked about yesterday. Okay, the limit is just a height that a function intends to get to. Okay, it's trying to get to a certain height. It's trying to get to a certain y value. Okay, it's intending to get there. And we're trying to figure out what that height is. The existence of the limit, as we get near to the x value, never depends on if there's a point there at that location or not. It only depends on, are we moving toward the same height from the left and the right? Are we moving to the height from both directions at that point? And if we do, we will have a limit. Now, if you think about that, what that means is there's 2 major cases where limits will exist and 2 major cases where limits will not exist. And that's why I really like this GIF so much that we looked at yesterday. It shows all 4 cases. It starts with continuity. Here comes continuity right now. Certainly a limit exists there. What if there's a removable discontinuity? Yes, the limit still exists. Now notice that it says that f of a itself does not exist, but the limit is still L. Uh-oh, now we have a jump discontinuity. So now the limit does not exist. We're not moving towards the same height. And if we have the infinite discontinuity, then we we also are not moving to the same location. We have a non-existent limit, no limit. Okay, so those are three of the main types of discontinuity. Removable, the limit does exist. Jump, it does not exist anymore because we're moving to two different heights. And infinite, it definitely does not exist because infinity is not a real number. Limits have to be real numbers. The fourth type of discontinuity, just as a reminder, was the oscillating discontinuity, which we really won't get into very much, but certainly limits do not exist in that chaotic situation either. So one last time, continuity, limit exists. Removable, discontinuity, limit exists. Jump discontinuity, limit does not exist. And then infinite discontinuity, limit certainly does not exist. Those are really the four major types of situations that we are going to evaluate. Now, we can always use substitution when it's continuous, but you cannot use substitution for holes. Okay, we'll usually get 0 over 0, which you can't evaluate. You definitely will have an issue if there's a jump discontinuity. I mean, I guess you could evaluate a one-sided limit, but not a two-sided limit, and then because it doesn't exist. And then, of course, there is no limit also with infinite discontinuity. So let's move on. You have two built-in examples on page 4. I'm actually going to do the second one first because it's the most similar to the example that we looked over at the beginning of this problem 20 from yesterday. It's just algebraic in nature. I cannot evaluate this example through substitution. If I put a 3 into this function directly, if I put a 3 in here, and a 3 in here, and a 3 in here, I would get 9 plus 3, which is 12 minus 12, so that's 0, over 3 squared, which is 9 minus 9, which is 0. So you can see, anytime you get a 0 over 0, that's indicating some type of hole situation. And if I look at the graph here, I definitely see that at 3, there is a hole sitting there. Okay, what height is that hole? Because the left limit and the right limit are both approaching that same height. So the limit is going to exist at that point, but I can't find it through evaluation. Now it looks like we found it was 1.17 rounded off to 2 decimal places. We usually like to round it off to 3, so I think it would be 1.167. You could kind of estimate it, I guess. It's definitely between 1 and 2, right? You could zoom in, or if it was on your calculator and get really close to it, it might be easier to use your table of values to do so. Okay, you can see that as we get really, really close to 3m, 1.1669, 1.1664, you can see how close they are getting to 1.166, something between a 4 and a 9, right? Like I mentioned, it was 7. But you need to know how to do these algebraically. And so let's take a look at the algebra. A lot of it goes back to what we did in Unit 1 with rational functions. We did a lot of factoring. The top is a trinomial that factors into 2 binomials. The bottom is perfect squares. Okay, so we factor, and remember, when we have canceling factors, it indicates a hole. So there's going to be a hole at positive 3. Now there would be a vertical asymptote at negative 3, right? This is negative 3, and there's a vertical asymptote at negative 3 right there. But we definitely get a hole at positive 3, and the graph and the table both indicated that. Now, if you remember how we evaluated the height of holes back in Unit 1, when we did all those rational functions, we just plugged the value of the hole into what we call the reduced equation. The reduced equation is where we get rid of the t minus 3's. So now when I plug a 3 in, I just get 3 plus 4 over 3 plus 3. This is a very important step right here. It's called the evaluation step, and there's your 7/6. I'm going to start pointing out some notation to you. This is really important. You have to carry this limit notation right here. until you evaluate. It's a common mistake, and people do lose a lot of points on this. They just use it on the first step and then it disappears. You have to maintain the limit until you've taken the limit. Okay, so the limit stays here, the limit stays here. Even at this step after I cancel these, the limit's still there. Why? Because I haven't evaluated it. See, the t's are still in here. But once I plug that 3 in, once I plug it in, see how the limit went away? There's no limit anymore. Where did it go? Well, we evaluated the limit, we've taken the limit. And a lot of people struggle with either not writing the limit long enough or writing the limit too long. We don't want to, continue writing the limit at this point right here because we've taken the limit. We're not taking the limit as t goes to 3 anymore here. That should not be there. Okay, so this is stuff that I really want you to practice tonight on problems 21 through 30, writing the notation correctly. When do I need to write the limit? When can I get rid of the limit? Okay, but you can see it's just algebraic. We cancel out the problem, which was the denominator, and then we can use substitution. Now, example 1 was a little different because we can't really use algebra. And so we're going to go back to a problem we looked at yesterday when we were just talking about what limits were. And this is what it was. What is the limit of this function right here, sine of x over x, as we approach 0? Okay. And what we found through a picture yesterday is that we do have a limit because from the left and from the right, both directions, I'm approaching a height of 1. So it looked like the limit was going to be 1. And when we looked at the tables, right, we saw that if we came in from the left, getting really, really close, and as we came in from the right, getting really, really close, those numbers are getting closer and closer to 1. So even though we got an error at 0 because it's undefined, we do have a limit as the heights converge towards 1. Okay, so we need to know this. This is a fact that is going to be really important. In fact, it's so important that we're going to call it an identity. Okay, let's put a big ol' star next to it. You're going to use this quite a bit on some of your limit problems that have trig functions embedded in them. It's a substitution. Okay, and in fact, it's expandable. I mean, we don't really have a way of evaluating this right now other than using pictures and using tables, but we're going to use this identity, and it's expandable to the fact where if you have a constant inside the sine function, so like a 3, and then you have the same constant underneath the fraction with the x in the denominator, but it has to be the same. So it could be like a 3x down here. It still is going to be equal to 1. You can test that on your calculator. For example, let's plug in our equation. Sine of x divided by x. And there it is. And we certainly don't need very much of a y-scale on this. So let's go in and kind of reduce it down to, maybe negative 1.5 to 1.5. And so there you can see it doesn't show the hole here at 1, at 0, 1, but we definitely know there is one. We could always use tables if you wanted to take a look at that, and let's go by, I don't know, let's go by, let's go by 0.01s. That should be a really good one. Okay, and let's expand it a little bit. And we should be zooming in on 1. Now it looks like we're not, so I'm guessing that I may not be in the right mode. It's kind of weird. Let me check that out for a second. Yeah, so even though my grapher is in radians, look at this, calculators in degrees. So let's fix that really quick. We'll go into settings and status, document settings, and get into radian mode. And now I'm in radians. That should help us fix this. All right, so now we see that we're in radian mode, and I just had to close the table and then open it back up, and you can see that it put these values into the correct ratios, and you can see how close they are getting. 2, 1, as the x values get really close to 0, which were undefined there, but that's okay. Now here's what I wanted to show you. I'm going to go ahead and swing this out a little bit, and let's go into our function, and we're going to do well, I guess we don't need the table anymore. So let's get rid of the table. And we just need the equation. So I'm going to plug a constant in here, like a 5, and I'm going to plug the same constant in the denominator with a 5. Now, you should see the graph change. In fact, maybe we'll leave this one alone, and we'll put a new one in that is sine of 5x over 5. So you'll see that the function is, you know, decreasing more quickly as we go out, but what is happening as we approach 0? That's the big question. And what you'll see is, look at that, it is approaching 1 still. So as long as you have sine of kx over kx, you're still going to get 1. And we can take a closer look at this really quick if you like. Zoom box. I'll just kind of zoom right through here, and you can see how we're approaching that 1. So very important relationship to know is this one. Now, here's an interesting question. What happens if I don't have the k on the bottom? Well, if you don't have the k on the bottom, what we're going to find is we have to do just a little bit of algebra. We have to get the k on the bottom. We have to multiply the bottom by k. But we can't just multiply the bottom of a fraction. We have to multiply the top by the same to keep it equivalent, right? That's like how 1/2 becomes, say, 3/6 as we multiply the top and the bottom both by 3. Because k is a constant, I can end up taking it out using the properties of limits. And so what's going to happen is that this is going to turn into a 1. And then I'm going to multiply that by k, and I'm going to get an answer of k. So it's a really simple little trick. If you ever need to do that, you just multiply by k, you factor it out, and then you're good to go. So this is a trick we need to use on this problem. Now this problem has a tangent in it, and not a sine, but we can fix that here in just a second. Let's start off by looking at the graph. What is happening to tangent x over x as we approach 0? Well, that zooms in on this part of the graph right here, and it certainly appears that both from the left and from the right, I am moving towards a height of 1. It looks also like the table verifies this. Look how close. In fact, by the time I get within 1/100th of 0, our calculator is so close to 1 that it is just rounding it off to 1. It's not actually equal to 1 there, but it's really, really close to 1. Now, undefined at 0, yes, but we're approaching a height of 1. How could we prove this using algebra and substitution? Well, the first thing is that I'm going to take this x and turn it into a fraction. So I'm multiplying by tangent of x because I need to turn that tangent of x into something I can work with. Like how about sine of x over cosine of x? See, now that I have that sign, I should be able to combine this sign right here with this x right here. So it's just a little refiguring, so to speak, of the fraction. I move the x over with the sign, and here they are. They're together again and happy. And I just move the 1 over cosine separately. Now I can use the properties of limits, specifically the multiplication property, to split this up into the limit of this times the limit of this. And then this is our identity. The limit as x approaches 0 of sine of x over x is 1. Okay. Meanwhile, I don't have an identity for 1 over cosine of x, but cosine of 0, so I had to plug the 0 in. That's called evaluating the limit. The cosine of 0 is 1. So really, I'm just going to get 1 times 1, which is 1. So the work confirms what we're seeing with the pictures. It just took a second to get to that point. I do want to point out one really common mistake, and it's in this section right here where I go from here to here. Okay, what I see way more often than I'd like to see is I see people who write this right here as the limit as x goes to 0 of 1. So they're basically turning the sine of x over x into a 1, and that's never true. Sine of x over x is never equal to 1. It approaches 1, but if we go back and we look at that picture of it, it never actually achieves a height of 1. It only has a limit of 1. And so you have to be really careful that when you make this substitution, this sine of x over x doesn't become a 1. The whole thing, the entire limit becomes a 1. That's the substitution. So start working on that immediately tonight, and hopefully that saves you some confusion down the road. Example 3 is just more properties of limits like we were looking at yesterday. It looks like example 1, or example A, I should say, uses the addition property of limits where I break it into the limit of f of x plus the limit of 4. Now, the limit of f of x is up here defined as 2, so I can substitute that for 2. And then the limit of a constant is itself, so the limit of 4, regardless of what x approaches, is 4, and so you get an answer of 6. Here's a problem where we use a division property. Limit of g of x over f of x can be split into the limit of g of x over the limit of f of x. Notice that we have to be approaching the same value. X is approaching 3 in both cases, and that's what x is approaching in our substitution. So we can now substitute, -1 for limit of g of x and 2 for limit of f of x. Finally, we use the multiplication property in the last example, and we split the constant out. Now, I will say that if it tells you to apply the properties of limits, you will have to do it this way. You will actually have to write the limit of 2 times the limit of f of x. But in your standard homework, or even on quizzes, I'm going to let you guys do it a little more loosely. I will let you take something like this and just pull the constant out and not have to evaluate the limit at a constant, since we already know that the constant's just going to become a constant. So this would be step 1, and then you can make your substitution after that. Okay. I think that's the end of the examples on that page. But I do have some bonus examples because there's so many variations of these problems. I think the more examples we can do, the better. So I'm going to post a PDF of these worked out on Calendar, as well as on Classroom. But I would definitely try working these out. I don't know if these are in your workbook. I may have at some point put them in there, but if not, just on a separate sheet of paper, you can pause the video, write them down, and then work these out. The first half of these are going to be very algebraic, kind of like problems 21 through 25 will be on your worksheet tonight, and then the second ones will be using those trig identities. 26 through 30 will be using that sine of x over x trig identity. Okay. So let's get to work. Pay attention to my notation. I'm going to really try to illustrate these the way that they have to be worked out. I cannot plug a 3 in. I mean, you could always try, but 3 cubed is 27, so I'm going to get a 0 on the top. 3 squared is 9, plus 2 times 3 is 6, that's 15, minus 15 is 0, I'm going to get a 0 over 0. So can't do that. 0 over 0 almost always indicates, though, that you have a good chance that a limit exists, because it's probably a removable discontinuity caused by a hole. So it looks like these are factorable expressions, and so what I'm going to do right off the bat is try some factoring, just like rational functions back in Unit 1. Okay? The top is difference of cubes, so that's x minus 3. 3 is the cube root of 27, and then the formula is square the first part. This is always the opposite of the binomial, right? These always match, so this is subtraction, this is subtraction. But this is the opposite of that. Multiply the two pieces together, so that would be 3 times x, and then square the second part of the binomial, which is 9. So that's how your function would work out. Now, the bottom is just a trinomial into a binomial. X times x is going to give me x squared. What numbers multiply to 15 but have a difference of 2? I believe it's going to be a 5 and a 3, so probably plus 5 to get the positive 2 in the middle, minus 3. And there is your removable discontinuity right there. It's the canceling factor that causes the hole, right? And so once I get rid of that, I should be able to evaluate it by plugging in a 3. So 3 squared plus 3 times 3 plus 9 over 3 plus 5 is 9 plus 9 plus 9 over 8, or 27 eighths. That's your answer. Notice that the limit that I wrote here disappeared as soon as I evaluated the limit. Okay, that's when you can get rid of the limit notation. The problems 21 through 39, I highly suggest that you graph these to confirm. Once you get your algebraic answer, graph them so you can confirm that yes, my graph is from both sides. As I approach 3 is approaching 27 eighths, which is a little more than 3, right? 3 and 3 eighths. Okay, 3.375, I believe, as a decimal. All right. Okay, these are the kind, very similar. You see a lot like this. They're going to make some of those of you that really hate fractions not very happy, because it does involve some algebra to get rid of the fractions. Once you've done a couple of them, though, they all work the same. So you just got to get used to the fact that you're going to have to deal with fractions. Once you know how to do that, one of these, you know how to do them all, though. So stick with them. Now, here's my my first thing. Okay, if I plug a 0 in, I'm going to get a 1/5 minus 1/5, which is 0 over 0. 0 over 0, once again, it's not an answer. So what I'm going to try to do is I'm going to try to get rid of the complex or compound fractions. I am going to figure that the common denominator of the two fractions is 5 times x plus 5. And so I'm going to multiply the top and bottom of the primary fraction by that common denominator, 5 times x plus 5. And this is where a lot of you guys I know will get stuck. Now, you could get a common denominator. Instead, you can multiply this guy by 5 over 5 and this guy by x plus 5 over x plus 5, and then get one fraction on top and then multiply by the reciprocal of x, and it'll still work out for you, but it's much slower process. So this is the way that I would recommend you do it. I have to distribute. This is where the mistakes are usually made, is distributing this through here. And you just got to practice and pay attention to the details. When I multiply by 1 over x plus 5, the x plus 5s are going to cancel. I'm just going to get a 5 times 1. When I multiply the 5 times x plus 5 times the 1/5, the 5s are going to cancel, and I'm just going to get an x plus 5. Now this is huge. Notice I put my x plus 5 in parentheses because I'm subtracting it. If you forget to distribute that, you're in trouble. Now this is another problem. People forget to multiply the bottom. Okay, you have to write that you're multiplying the top and the bottom. Algebraically, that's the only way it's accurate. Okay, but people just forget to multiply the bottom, and then you still have a 0 in the bottom, and you're in trouble. See, if you do it the right way, look what happens. Your 5's cancel out, leaving you just with a negative x over 5x times x plus 5. And because this is just multiplication here, I can cancel this x with this x, leaving me with just the limit as x approaches 0 of negative 1 over 5 x plus 5. You can multiply that out to 5x plus 25, but it's just as easy to leave it. We got rid of the one thing that was killing us from the beginning, which was this dude right here. We couldn't plug a 0 into that. And it was around, and it was around, and it was around, but then we got rid of it right there. That, as soon as you get rid of that, that means you can just go into evaluation mode. I'm going to plug my 0 in. Okay, so negative 1. What's 5 times 5? 25. Negative 1/25 is your answer. Graph it and confirm that you're really, really close to 0 when this function approaches 0. Negative 1/25 is like 0.004. Okay, or 0.04. Sorry, 0.04. Negative 0.04. All right. This is just like the example we started today's lecture with. It's same problems, just different numbers. The one thing that is really going to be something you're going to have to be careful about is your algebra, because when you expand, and you could try to put a 0 in here, but you're going to get 6 squared minus 36, which is 0 over 0. It doesn't work. You're going to have to expand this. And so many people want to just say, oh, well, that's 36 plus x squared, right? No, it's actually not, okay? You can try to make a plus b squared, a squared plus b squared. You can try to make it happen, but no matter what, it is not going to happen. It's just not. So quit doing it and move on, right, with life. You have to FOIL that out. It has to be 6 plus x multiplied by 6 plus x. So you are going to get a 36. You're also going to get a couple 6x's in the middle, and then you'll get your x squared. And so you can see how this works out so very closely to the same as what we had before. The constants cancel. I can factor out the x. I get 12 plus x left, which cancels that x in the bottom. What did I want to get rid of to make this thing work? This dude. That's why I couldn't substitute, right? Well, guess what? It's gone now. That means I can just substitute 12 plus 0. You have to show this step. I know that some people are like, dude, 12 plus 0 is obviously 0. Why do I have to show, this step right here? Because substitution must be shown. When you evaluate a limit, it's through substitution. No matter how simple it is, if you don't show that, you're going to lose points. I hate to say that, but that's the way the AP does it. That's the way it gets done. So please remember that. All right, so now we shift into the trigonometric type style questions, and what we're looking for is that sine of x over x identity. Okay, so I almost have the identity right here, except I have a 7 in here, so I would need to put a 7 down here in the denominator to make it fit the identity. So let's go ahead and do that. Let's go ahead and put the 7 down here. Perfect. But then I have to put the 7 up here, okay? Because that balances it out. 7 over 7 is 1. I'm really just multiplying that by 1. So now I can pull this 7 out. That's the top 7. Notice I'm not going to make you write limit of 7 because I think constants are obvious to work with. If it does say use properties of limits, you will have to do that extra step, sorry to say, but usually you're just evaluating them. And this is the thing that we were looking for, that sine of kx over kx that I hope you wrote down in your notes from a couple slides ago. We can now substitute that in, and it's going to be 7 times 1, not limit of 1. Remember, Sine of 7x over 7x is never equal to 1, but the limit of 7x over 7x, sine of 7x over 7x approaches 1. So your answer on this problem is 7. You could verify that one on your calculator. This one has that sine x in it, so I'm immediately going to start trying to find that x. I don't think I need to introduce an x this time. I think I just need to do some factoring in the denominator. I'm going to factor out an x, leaving me with 4x minus 3. And now I need to use the property of limits. I'm going to use the multiplicative property of limits, which tells me the limit of f of x times the limit of g of x is equal to the limit of f of x times g of x. So I'm going to split the identity I'm really wanting to get, sine of x over x, using multiplication, because this is multiplication, right? You have to write your limits both times, otherwise it's not correct. So you can't just write the limit once, or you haven't really split the limit. This whole thing turns into the 1 that we were trying to get through identity. This has to be evaluated. So we're going to do 4 times 0 minus 3. Notice that I didn't write the limit anymore because I plugged the 0 in. That's when you can stop writing the limit, is after evaluation. So this is going to be 1 times 1 over negative 3. So our answer on this problem is negative 1/3. We couldn't have got that by plugging a 0 in. We would have got a 0 over a 0. That doesn't tell us anything. The graph will confirm that this function approaches negative 1/3 as x approaches 0. So graph it, check it out, and you'll see that. Here's one that I think we're going to have to split not through multiplication, but through addition. So we'll use the limit property of addition. So we'll do sine of 4x over 4x. That looks great, right? Plus the limit, as x approaches 0, of 8x over 4x. Don't forget the common denominator. When you split a fraction, you have to split it using the common denominator. So this is perfect. It's ready to turn into a 1. This, if I try to plug the 0 in right now, I run into a problem because I get 0 over 0, right? 8 times 0, 4 times 0. But remember, those cancel. And I think 8 over 4 is just 2, and the limit of a constant is just a constant. So it looks like on this problem, we're going to approach a 3, and you can confirm that once again on your calculator. All right, so we finally made it through all those examples, and hopefully those help you out in tonight's homework, especially 21 through 30, which will be the ones that I will want you to write out really nicely and submit. If you need help with that, there's a little tutorial link on Classroom, but just either scan them into your computer for the best quality, or at least use a scanning app. There's a lot of free scanning apps you can use on your phone, or worst case scenario, just take a picture of it on your phone and then attach that to the assignment, and I will take a look over those, and that's it. I don't need all 21 through 48. I really just need 21 through 30 submitted. There's a really good website I like. They have a lot of lectures. They have some higher level calc stuff, but they used to have these awesome limit tutorials, and I haven't been able to find them anymore. But they do have some good long lectures on limits if you want to see some more. The guy writes a lot of calculus books. He wrote the book, like the Calculus for Dummies book. So he has a really good way of breaking it down into simple English. His name's I think Michael Kelly. But check it out if you need some extra help. And I think that's about it. Good luck with your work today. I'll be around at 3 if you have questions regarding limits. Good luck.